Hey guys, good evening and welcome back again to your Unacademy NEET English channel. I hope all of you are doing great, having a good time. So people, quickly let me know in the chats if all of you can hear me, if I'm perfectly audible and visible to every one of you. Let me know quickly in the chats. Everyone. Let me know quickly in the chats if all of you can hear me, if I am perfectly audible and visible to every one of you. Good evening, people. Good evening and welcome back. Good evening and welcome back. Yeah, I believe everything is super clear, right? Everyone. Yeah, it's absolutely clear. Perfect, perfect, perfect. So my dear students, as you all must be knowing, today we are going to start one new chapter, which is of your class 12th chemistry, right? And the name of the chapter is Chemical Kinetics. One of the super important chapters, right? When it comes to your physical chemistry. And my dear students, every year you can expect like 2-3 questions from this particular chapter in your NEET examination as well. Okay? And before starting this particular chapter, I hope you all know that. I hope you all know one thing. What is that? That is, yesterday I posted one video which was the complete GOC. It's a one shot, guys, detailed one shot wherein all the concepts of general organic chemistry have been discussed. You can watch, you can consult this particular video for your GOC. And 2 days back, one more video I posted over here. This was your chemical bonding one shot. Again, a detailed one shot wherein every single thing related to chemical bonding is discussed, right? So these 2 chapters you can consult from the recorded portion, okay? These 2 chapters you can consult from the recorded portion. One is your general organic chemistry and another one is your chemical bonding. And today, what exactly we are going to start? As I told you already, we are going to start the chapter Chemical Kinetics, which is basically the chapter of your class 12th chemistry. Okay? Just give me a second. Just give me a second. All right. So people, should we start then? All ready? All ready? And let me tell you, this particular chapter I'll be completing exactly in 3 sessions. Okay? In 3 live sessions, I'll be completing this particular chapter in detail, in depth. Okay? Every single concept which can be asked from this particular chemical kinetics chapter, I'll be covering all the concepts, right? All the problem patterns, entire theory in detail. No, this is not the one shot. Today's session is not the one shot. This chapter of chemical kinetics I'll be covering in 3 parts. Today is part 1. On Tuesday, 7 p.m. it's going to be part 2. And then on Friday, it's going to be part 3. Right? So in coming week, this whole chapter is going to get completed. Exactly in 3 sessions. Today is part 1. Perfect. So should we start the session? All ready for it? All ready for it, people? I'll be starting exactly from the basics, from the scratch. Don't worry. Don't worry. Every single thing will be started from the scratch itself. Okay, well, I think there is one mistake here. This should be class 12th, but it's mentioned class 11th, right? So you can modify it. It's class 12 chapter. Even class 11 students can watch it also. No issues at all. Perfect. Chalo. Let's get going then. Let's get started with the chapter Chemical Kinetics. And let's try to kill this particular chapter as well. So my dear students, what this chemical kinetics exactly is all about? What all things we have to cover in this particular chapter? Let me start from the scratch itself. First of all, if I talk about chemical kinetics, what kind of information we get from the chapter Chemical Kinetics? Let's get to know that. My dear students, let me tell you, this chemical kinetics, it deals with the rates of the reactions, It deals with the rates of the reactions, number one. It deals with the factors. It deals with the factors that affect the rate of the reaction, number two. And it deals with the mechanisms involved in a chemical reaction. It deals with the mechanisms involved in a chemical reaction. So, my dear students, three things we have to discuss in detail, okay, in this particular chapter. This chemical kinetics, it gives us it is the branch of science that deals with the rates of the reaction. So, in this particular chapter, in detail, we are going to discuss about the rates of the reaction, right? You'll get to know why some reactions, they occur slowly, why some reaction occur fastly, what is the logic, what is the reason, etc., etc. Every single thing shall be discussed in this particular chapter. Number one, rate of the reaction, the speed with which the reaction takes place. Number two, what are the factors on which rate of the reaction depends upon? This is the second thing which we are going to discuss in this particular chapter. And the third thing, what are the different mechanisms involved in a particular reaction? So this chapter is all about these three major topics. One is your rate of reaction, factors affecting rate of reaction, and mechanisms involved in a chemical reaction. Okay? Now, before starting this particular chapter in depth, there are some basic things which you need to know. Certain basics which is required to start this particular chapter. In order to start this particular chapter, some basic terminology, some basic things, some basic concepts, they should be clear first of all, then only you'll find this chemical kinetics chapter absolutely easy, guys. Trust me on that, right? So try to understand what those basic things exactly are all about. My dear students, understand and remember. Understand and remember. I'm writing the point over here as, the point is like this. As the reaction starts, number of moles of reactants, concentration of reactants, number of moles of reactants, concentration of reactants, as well as the partial pressure of reactants. As well as the partial pressure of reactants decreases with time. Decreases with time. This is the first point which I want every one of you to take a note of. Okay? Whatever things I'll be mentioning on the screen, take a note of every single thing, because every single thing is going to be super important. The first point which I mentioned over here, as the reaction starts, number of moles of reactants, concentration of reactants, as well as the partial pressure of reactants, it decreases with time. Why it happens so, you'll get the idea in some time. Before getting the idea, one more point I'm going to write over here. And what is that particular point? I'll be writing, as the reaction starts, number of moles of products, concentration of products, as well as the partial pressure of products, partial pressure of the products increases with time. Increases with time. So first of all, let's try to understand these two statements in detail. Let's get to know the meaning of these two statements. The first statement is, as the reaction proceeds, moles, concentration and partial pressure of reactant decrease with time. Similarly, as the reaction starts, moles, concentration, partial pressure of products that increase with time. Right? These are two basic statements which I would want to cover over here first of all before starting the chapter. Right? So my dear students, for example, I'm taking a reaction like this. Let's say I've got the reaction A gives B. Right? For example, this is my reaction. A gives B. I'm assuming that this reaction is going to take place in a container. Assume that this reaction is going to take place in a container whose volume is, for example, V liters. This reaction is going to take place in a container whose volume is V liters, right? Now, my dear students, here I'm defining a term which I'm representing with square brackets. I'm defining a term which I'm representing with square brackets. Either you represent it with square brackets or you can represent directly it with C. And what is the C? C represents concentration. C or square brackets. It represents just the concentration. And how do we define the concentration? It is nothing. Number of moles divided by volume of the reaction vessel in liters. As simple as that. What does that mean? For example, if I write concentration of reactant, what is meant by concentration of reactant? Concentration of reactant means number of moles of reactant divided by volume of the vessel in liters, volume of the container in liters. If I, for example, write concentration of products, how do I write it? Number of moles of products divided by volume of container in liters, right? Now, my dear students, one thing which I believe that you would have studied in your class 11th mole concept, which I have taught you here also, right? I am pretty much sure you would have seen that. What is that point? Since you know, as the reaction proceeds, or let me just make you understand like this. Let's assume that this A is right now in gaseous phase. Imagine that B is also in gaseous phase. Imagine that B as well as A, they are in gaseous phase. So at time t is equal to 0, at time t is equal to 0, when the reaction has not started, at time t is equal to 0, when the reaction has not started, when this reactant has not got converted into the product. I'm talking about the initial conditions. At time t is equal to 0, when the reaction has not started yet. I would say at time t is equal to 0, number of moles of reactants in the container, they'll be maximum. And number of moles of products initially at time t is equal to 0, that is going to be 0. This is something which I believe every one of you would be knowing. Initially, in the container, there will be maximum moles of reactants, right? There will be minimum moles of products, 0 moles of products, because the reaction has not started yet. Now, my dear students, as the reaction starts, what happens to the moles of reactants? Moles of reactants decrease with time and moles of products, they increase with time. As the reaction starts, as A starts getting converted into B, number of moles of A, they'll keep on decreasing with time, and number of moles of B, they'll keep on increasing with time, right? Now, my dear students, as the number of moles of reactant decrease with time, therefore, I can say concentration of reactant decreases with time as well. As the reaction proceeds, I would say concentration of reactant decreases with time as well. In the similar way, since number of moles of products increase with time, right? Therefore, concentration of product, this also increases with time. Perfect. Number of moles of reactant are going to decrease with time. Number of moles of product are going to increase with time. Concentration of reactant is going to decrease with time. Concentration of product is going to increase with time. Right? Now, my dear students, one more thing which I would want to let you know right now. What is that? Just understand. Initially, at time t is equal to 0. At time t is equal to 0, there is only reactant in the container. There is no product. So if I ask you, initially at time t is equal to 0, how many gases will be there in the container? I would say at time t is equal to 0, there will be only one gas in the container. That is gas A. At time t is equal to 0, there will be only one gas in the container. That will be gas A. Because B has not got formed yet. Okay? So initially at time t is equal to 0, whatever will be the total pressure, that is entirely going to be due to A. Right? That's entirely going to be due to the A particles. Now, my dear students, we know the number of moles of A, they are going to decrease with time. If number of moles of A are going to decrease with time, if number of moles of B are going to increase with time, what does that mean? That means gas A molecules are decreasing with time. Gas B molecules are increasing with time. So, can you let me know what will happen to the pressure due to reactant? Initially, whatever was the pressure, that was entirely due to A. Now the moles of A are decreasing with time, right? Moles of A are decreasing with time. So pressure due to A will be decreasing as well. Pressure due to A will be decreasing as well, which is what you call as partial pressure, right? So partial pressure of A decrease with time. Now number of moles of B increase with time. If number of moles of B increase with time, what does that mean? That means pressure due to B, that also increase with time. So I would say partial pressure of B increases with time, right? So I believe these two statements are absolutely clear to you. As the reaction starts, moles of reactant, concentration of reactant, as well as partial pressure of reactant, it decreases with time, right? Similarly, moles of product, concentration of product, as well as partial pressure of product, it increases with time, right? So if you would want to plot these graphs over here, just to understand these two statements, if you want to plot graphs, I can make you understand over here with the help of graphs as well. Okay, for example, you are plotting a graph which is between concentration and time, right? You are plotting, for example, a graph between concentration and time. My dear students, at this particular point, the value of T is 0. The value of T is 0. What does that mean? That means the reaction has not started yet. So in the container, there will be only reactant. In the container, there will be only reactant. And as the reaction proceeds, moles of reactant, concentration of reactant, as well as partial pressure of reactant, that decrease with time. Over here, I'm plotting a curve between concentration versus time. And we know as the time proceeds, concentration of reactant, it decreases with time. Perfect. So this particular graph, it is basically valid for what? It is basically valid for reactant. Okay. This particular graph is valid for the reactant. Similarly, my dear students, if you want to plot a graph for the products, you should be in a position to make a graph for the products as well. Say, concentration versus time. Concentration versus time. Okay. This is time t is equal to 0. At time t is equal to 0, there is only reactant in the container. Concentration of product at time t is equal to 0 in the container will be 0, right? And with time, what happens to concentration of product? It increases. So this particular graph, it is basically valid for products. My dear students, this is not only the graph between concentration versus time. This same is going to be the graph between moles of reactant versus time as well. Same is going to be the graph between partial pressure of reactant versus time as well. So this is not just one graph. These are technically three graphs. Moles versus time, concentration versus time, and partial pressure versus time. And all these three curves over here, they are valid for the reactant. Similarly, this particular graph, which is about the product, it's not only about moles, it's not only about concentration versus time. The same is going to be between moles versus time, same is going to be between partial pressure versus time for the products. So in total, these are not just two graphs now, these are in total 6 graphs, right? So I just want you guys to remember two statements. When the reaction starts, moles of reactant, concentration of reactant, as well as partial pressure of reactant, that decreases with time. Moles of product, concentration of product, as well as partial pressure of product, that increase with time. If these two statements are clear to you, let me know once in the chats with some thumbs ups quickly. Then only I can start the chapter. Quickly, people. Everyone in the chats. All clear? Perfect. I believe this part is clear to everyone, right? Now, let's get going with the first topic that we are going to cover over here. What is that going to be? That's going to be average rate of the reaction. Average rate of the reaction. Let's try to understand what this average rate of reaction is all about. Try to understand carefully, guys. See, let me first of all mark its definition. Average rate of reaction. It is defined as average rate of reaction. It is defined as change in the concentration of either reactant or product. Change in the concentration of either reactant or product in a given interval of time. in a given interval of time. Average rate of reaction, which I'm denoting with RAV. I'm denoting it with RAV. It is defined as change in the concentration of either reactant or product in a given interval of time. What does that mean? Before letting you know the meaning of this particular definition, let me exactly tell you how do you write it mathematically. I'll say average rate of reaction. I'll start with plus minus. Why plus minus? What is its significance? You'll get the idea in some time. Plus minus change in the concentration of either reactant or product divided by the time interval. Change in the concentration of either reactant or product divided by time interval. Let's try to understand this average rate of reaction in detail now. Okay? Let's try to understand this average rate of reaction in detail now. See guys, for example, imagine that you've got a reaction over here. Let's say the reaction is A gives B. Let's say the reaction is A gives B. I'm assuming this reaction will be taking place in some closed container, right? Imagine that this reaction is taking place in some closed container. For example, if I write time t1, let's say at some time, this time can be 5 seconds, 10 seconds, 20 seconds, whatever time. At some time t1, for example, I calculated the concentration of reactant in the container and the concentration of product in the container, for example. And for example, I got to know the concentration of reactant at time t1, that is equal to C1. The concentration of product at time t1, let's say that is equal to C3. For example, I'm just giving you the random values. Muntazir, chemical bonding one shot I have posted. You can go to the video section. I showed you a few minutes back. See, this is the point why I don't want you guys to join late. See, you are again asking about the chemical bonding. Here I have posted chemical bonding as well as GOC. This is one shot, complete detailed one shot of chemical bonding here. You can consult bonding here, right? And this is your GOC, complete GOC, right? Okay, chalo, let's move on now. Okay, so my dear students, I took a reaction A gives B, and I'm assuming that concentration of reactant at time t1 is C1, concentration of product at time t1 is C3, for example. Now we know as the reaction proceeds, what happens to the concentration of reactants? Concentration of reactant decrease with time. Concentration of product increase with time. Let's say at some time t2. Concentration of reactant, I again calculated, it came out to be C2. And concentration of product at time t2, it came out to be C4. So I'm giving you certain values over here. For example, at time t1, the concentration of reactant was C1 and the concentration of product was C3. Okay. At time t2, the concentration of reactant is, for example, C2 and the concentration of product is C4, right? Now, my dear students, something which we already know. As the reaction starts, concentration of reactant keeps on decreasing and concentration of product keeps on increasing. So, if I compare these two values, C1 and C2, can I say C2 value will be less than C1? Absolutely, C2 will be less than C1. Similarly, this C4 will be greater than C3, right? C2 will be less than C1 and C4 will be greater than C3. This is something which we already know. Okay. For example, I want to calculate the rate of the reaction in this particular time interval. In this particular time interval, which I'm representing with delta T. In this particular time interval, T1 to T2. This time interval I'm representing with delta T. Let's say I want to calculate rate of reaction in this time interval T1 to T2. Okay. Whenever rate is measured in a given interval of time, you call that rate of the reaction as average rate of reaction. So basically, I'm asking you to calculate average rate of this reaction in the interval delta T from T1 to T2, right? Now, as per the definition, average rate of reaction is defined as change in the concentration of either reactant or product in a given interval of time. So basically, average rate of reaction you can calculate with respect to reactant or you can calculate it with respect to product. Average rate of reaction you can calculate with respect to reactant as well as with respect to product. For example, if you are calculating average rate of reaction with respect to reactant, imagine that you are calculating average rate of reaction with respect to reactant. How exactly I'm going to calculate it? Average rate of reaction with respect to reactant will be equal to change in the concentration of reactant. Change in the concentration of reactant. How much concentration of reactant is changing from C1 to C2? So what will be the change in the concentration of reactant? It will be C2 minus C1 divided by, what is the time interval here? Time interval is delta T, which is nothing but T2 minus T1. Average rate of reaction with respect to reactant will be equal to change in the concentration of reactant, which is final concentration of reactant minus initial, divided by time interval, which is just T2 minus T1. Similarly, my dear students, if you want to calculate average rate of reaction with respect to products, you can do that as well. So what you need to do? Change in the concentration of products, which is C4 minus C3. C4 minus C3 divided by time interval is the same, which is T2 minus T1. So here you are calculating average rate of reaction with respect to reactant. Here you are calculating average rate of reaction with respect to product. But, my dear students, if you look at one simple thing, as I told you already, C2 is less than C1. C2 is less than C1. If C2 is less than C1, the difference between these two, what is it going to come out to be? Positive or negative? I told you already, C2 is less than C1. If C2 is less than C1, therefore C2 minus C1 will come out to be negative, right? C2 minus C1 will come out to be negative. If C2 minus C1 comes out to be negative, what does that mean? That means the rate of the reaction is coming out to be negative. Rate, speed is coming out to be negative, right? Is that possible? Can the rate of the reaction, can the speed with which the reaction is taking place, can it be negative? It can never be negative. It can never be negative. But over here it's coming out to be negative. So what I need to do is, I'll be multiplying with the minus sign in the beginning, then only this minus and this minus over here will come out to be positive at the end. Okay? So I hope you got to know why am I multiplying with this minus sign over here. Because if I'm not multiplying with the minus sign, rate is coming out to be negative and rate cannot be negative. So we have to make that positive somehow. How exactly? You just have to multiply with the negative sign. That's all. Rate of the reaction with respect to products is equal to C4 minus C3. C4 is greater than C3. C4 is greater than C3. Therefore, the value already comes out to be positive only. Right? So you need not to multiply with the minus sign. That means you'll be multiplying with the plus sign. Rest everything is same. Okay? So my dear students, if you look carefully, I had made a formula over here. Average rate of reaction is equal to plus minus. I hope you got to know why am I writing plus and minus over here. I hope you got to know why am I writing plus and minus over here. Plus and minus, change in the concentration of either reactant or product in a given interval of time. Right? I believe this is clear. I believe this is clear till here. Okay? Now, my dear students, remember from now onwards, whenever average rate of reaction is to be calculated with respect to reactant, you'll be always starting with the minus sign. Whenever average rate of reaction is to be calculated with respect to reactants, you'll be starting always with the minus sign. Then you'll write change in the concentration of reactant divided by time interval. That's all. Yeah? Right? In the similar way, if you want to calculate average rate of reaction with respect to products, you will have to start with the plus sign, change in the concentration of product divided by time interval. Now this minus and plus over here, it has got further some more significance. The minus sign with which I'm multiplying over here, it indicates that the concentration of reactant decreases with time. This plus sign indicates that the concentration of products increases with time. I believe I'm clear to every one of you. Okay. Now, my dear students, let's have a look on its graphical approach. Let's try to understand this average rate of reaction graphically. Let's try to understand this average rate of reaction graphically. It's simple, guys. Just have proper concentration on the screen. This chapter you'll find very easy. For example, I'm making a graph over here. The graph is between concentration versus time. Concentration versus time. And I'm making the graph like this. Okay, I'm making a graph like this. So with time, concentration is decreasing. And we know concentration of reactant decrease with time. So this particular graph is valid for what? This particular graph is valid for reactant. Okay, it's valid for reactant. Similarly, I'm making one more graph. It's again between concentration versus time only. Concentration versus time. And the graph is like this. So with time, concentration is increasing, and we know concentration of product increase with time. We know concentration of product increase with time. Now, my dear students, look at the time interval which we have chosen over here, T1 to T2. T1 to T2. Let's say this particular point over here represents T1 and this particular point represents T2. Okay, one is T1, one is T2. Now, at time T1, what was the concentration of reactant? At time T1, what was the concentration of reactant? Check it out. At time T1, the concentration of reactant was C1. So basically, this point here represents your C1. Now, similarly, at point T2, what is the concentration of reactant? So at time T2, the concentration of reactant is C2. So this point represents your C2. Correct? Which time interval exactly am I talking about? I'm talking about this particular time interval, which I'm representing with delta t, and delta t is nothing but it is T2 minus T1. So this particular time interval I'm talking about. So right now, I want to calculate average rate of reaction in this time interval. Okay? How exactly you're going to do it? You just are going to write average rate of reaction is equal to change in the concentration of reactant. What is the final concentration of reactant? See, at time T1, this is initial concentration. At time T2, this final concentration. So final concentration of reactant minus initial concentration of reactant divided by time interval, that is T2 minus T1. But look at the graph, guys. C2 is less than C1. C2 is less than C1. If C2 is less than C1, the sign, the difference between these two, that's going to come as negative, but rate cannot be negative, so you have to multiply with the minus sign in the beginning, right? So this is how you are going to calculate average rate of reaction with respect to in terms of reactants. Okay, perfect. Similarly, calculate the average rate of reaction in the same time interval. Calculate the average rate of reaction in the same time interval, but with respect to products. See how exactly you're going to do it. Again, let's say this is point T1, this is time T1, and for example, this is basically time T2. Okay. Now, my dear students, at time T1, what is the concentration of product? At time T1, the concentration of product, how much was that? Look at the values. At time T1, concentration of product was C3. So this point will represent your C3. Similarly, at time T2, what is the concentration of product? Concentration of product was C4 at time T2. Again, my dear students, I'm choosing this time interval. This is the time interval which I'm choosing, which I'm representing with delta t, which is nothing but T2 minus T1. This is your time interval. Let's say in this time interval, again, I want to calculate rate of reaction. So I'm technically calculating average rate of reaction with respect to products, which will be equal to change in the concentration of product. See, this is the initial concentration of product. This is the final concentration of product. So final concentration of product minus initial concentration of product divided by time interval, that is T2 minus T1. Now you can look at the graph. C4 is greater than C3. If C4 is greater than C3, the difference between the two comes out to be positive. So what you have to do over here is you'll be multiplying with the minus sign. Okay? I believe I'm clear. Right? So graphically, this is how you calculate average rate of reaction with respect to reactants. This is how you calculate average rate of reaction with respect to products. One thing you just have to remember, when it comes to reactants, you start with minus sign. When it comes to products, you start with plus sign. Minus indicates that the concentration of reactant decreases with time. Plus indicates that the concentration of product increases with time. If I'm clear with this, let me know once in the chats with some thumbs ups. Quickly, guys. All clear? What did I mention here? Just a second. C1. C4, C3. Was this C4, C3? Yes. Correct, right? Let me know once in the chats with some thumbs ups if every single thing is clear till here. All clear? Should I move on? Should I move on, guys? And by the way, I'll be sending you the notes, handwritten notes. I'll be sending you the handwritten notes of this particular chapter in my Telegram right after this particular session. Okay? If you're not the part of Telegram, you guys can join in. That is Wasim Bhatt Chemistry Official. That is the name of the Telegram channel. Wasim Bhatt Chemistry Official is the name of the Telegram channel in which I'll be sending the handwritten notes. I'm moving on. I am moving on, guys. This was the first terminology which we have over here. That was your average rate of reaction, which we represent with RAB. Now, the second terminology is what you call as instantaneous rate of reaction. Instantaneous rate of the reaction. Instantaneous rate of the reaction. Okay? Instantaneous rate of reaction. I'm going to represent this with RINS. That's all. RINS. My dear students, how do we exactly define the instantaneous rate of the reaction? Let me write its definition, then I'll make you understand what it means. Instantaneous rate of reaction is defined as, change in the concentration of either reactant or product. Change in the concentration of either reactant or product at a particular instant of time. At a particular instant of time, or you can define it like this as well. Change in the concentration of either reactant or product at a particular instant of time, or you can say in a very, very, very small interval of time. In a very, very, very small interval of time. Let's try to understand this. My dear students, I believe in your physics you have discussed your average speed and instantaneous speed, right? How do you denote the average speed? Average speed you denote like this, delta x divided by delta t, right? Total distance divided by total time. This is your average speed, okay? Now, if you convert this average speed into instantaneous speed, what do? Do you make this time interval very big or very, very, very small? You are going to make this time interval very, very, very small, right? So I'll be using the limit over here and making this time interval very, very, very small. Delta t approaching towards 0. So time interval, which was this much in the beginning, now you're shrinking this time interval to delta t approaching to 0, right? Perfect. Now, my dear students, this is something which you call as instantaneous speed, right? And in physics, how do you represent it? dx upon dt. Perfect. Now, similarly, we are going to convert your average rate of reaction into instantaneous rate. How do we write the average rate of reaction? Average rate of reaction we write like this, delta C upon delta T. This is your average rate of reaction. If I use the limit and make this delta T approach towards 0, if I approach this delta T towards 0, if I'm decreasing the time interval, if I'm making the time interval very, 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 very small, if you look, time interval was big. Now make this time interval very, very, very small. Okay. Limit delta T approaching towards 0. Delta C upon delta T. Now you are going to represent it with dC upon dt. And my dear students, this is something which we call as instantaneous rate of the reaction. So in short, whenever you calculate rate of reaction in a bigger time interval, that's your average rate of reaction. And whenever you calculate rate of reaction in a very, very, very small interval, you call that as the instantaneous rate. That is the simple difference. Okay. And how do we represent this instantaneous rate? dC upon dt. How do you represent it? dC upon dt. dc upon dt. Now, my dear students, if you look here carefully, dx upon dt, what is its geometric interpretation? Slope of the tangent at a point on x versus time curve. Slope of the tangent at a point on x versus time curve. And this dc upon dt is what we call as slope of the tangent at a point. Slope of the tangent at a point on what? On concentration versus time curve. On concentration versus time curve, right? And geometrically, how do you calculate it? It is simply tan of theta. It is simply tan of theta. Now, let's try to understand this a bit more in detail. Before understanding this a bit more in detail, let's get to know it graphically. My dear students, what is the difference between average rate and instantaneous rate? When we calculate average rate of reaction, we keep the time interval large. When we use the instantaneous rate of reaction, that time interval delta t, that approach towards zero. That means now on the graph, it won't look like a time interval. It will look like a point. Okay? It's simple, guys. Look at this particular graph. This was the time interval in the beginning. It was a big time interval. Now make this time interval approach towards zero. So make it short, make it short, make it short, make it short. Make it short till this time interval, which used to look like a gap in the beginning. Now make it such small that it should not look like a gap. It should look like a point. I believe I'm clear with this, right? I believe I'm clear with this. So, for example, I'm making concentration versus time. Concentration versus time. Okay? First of all, if I ask you whether this graph is valid for reactant or product, with the time, concentration increases. So, this graph is valid for the product. Okay? Now, for example, I'm asking you to calculate the instantaneous rate of reaction in this time interval. It's a very, very, very small time interval. It looks like a point. So how do you do it? How do we calculate instantaneous rate of reaction? Slope of the tangent at a point on concentration versus time curve. This is your concentration versus time curve, right? Slope of the tangent. Let's do one thing. Let's draw the tangent at this point. When we draw the tangent at this particular point, we just need to get its slope. How do we get its slope? Get this angle first of all. It is theta, right? And tan of this theta is going to give us the slope of the tangent at this particular point. And slope of the tangent at this particular point, it gives me what? Instantaneous rate of reaction. So this is how I'm going to calculate instantaneous rate of reaction, right? Now tell me one thing. Is this theta acute here or obtuse? This theta is acute and tan of acute angles is positive. So instantaneous rate of reaction, it will come out to be positive only. It will be already coming out to be positive, right? It will be already coming out to be positive. That clearly tells you one thing, that you have calculated rate of reaction with respect to what? You have calculated this instantaneous rate of reaction with respect to products. That's why it came out to be positive. Okay? Perfect. Now, similarly, if I make one more graph like this, let's say I'm plotting one more graph here. The graph is like this. Understand carefully. For example, this is concentration versus time. Concentration versus time. Let's say the graph is starting from the top, coming downwards. So is this graph valid for reactant or product? Look carefully. With time, concentration is decreasing. With time, concentration is decreasing. So concentration decrease for reactant. So this graph is valid for basically reactant. Okay. Now I want to calculate instantaneous rate with respect to reactant. I want to calculate instantaneous rate with respect to what? With respect to reactant as well. Right? For example, in a very, very, very small time interval. Right? This is the time interval, which is very small, which looks like a point here on the graph. So what exactly am I supposed to do? I'm supposed to draw a tangent here. Once you draw a tangent at this particular point, this is, for example, the tangent, get its slope, get the slope of this tangent. How do you get the slope? In order to get the slope of this tangent, I'll be calculating this angle, which is theta, right? Get the tan of this particular theta. Get tan of this theta over here. Tan of the theta will give me the slope of the tangent at this particular point. Okay? And slope of the tangent on the concentration versus time curve at a particular point, what does that give me? That gives me instantaneous rate of reaction. Now think logically. Theta over here is obtuse, greater than 90, right? Greater than 90. That means theta lies in second quadrant. Theta lies in second quadrant. So tan of theta over here will come out be negative. But if tan theta comes out be negative, that means the rate is negative, but rate cannot be negative. So to make that rate positive, I'll be multiplying with minus sign in the beginning itself. So it's minus tan of theta, which will at the end come out to be positive. Right? So here I'll be writing plus minus. Plus when I'm calculating instantaneous rate with respect to product, minus when I'm calculating instantaneous rate with respect to reactant. Okay? Is it clear, people? I believe you got the exact idea about the instantaneous rate of reaction as well. So quickly, let me know once in the chats. I'm looking at your chats only. Everyone. Everyone, people. Everyone means everyone. Perfect, guys. Now, let's move on to one more topic. Let's move on to one more topic. What is that? That is going to be rate of reaction as per stoichiometry. Rate of reaction as per stoichiometry. My dear students, assume that you have got a balanced chemical equation like this. N1A plus N2B. It gives, for example, N3C plus N4D. This is, for example, a balanced chemical equation. N1A plus N2B gives N3C plus N4D. This N1, N2, N3, N4, they represent the stoichiometric coefficients of reactants and products. N1, N2, N3, N4, they represent the stoichiometric coefficients of reactants and products. Now, my dear students, as I told you already, as the reaction proceeds, what happens to the amount of reactants with time? Amount of reactants, moles of reactants, concentration of reactants, everything decreases with time, right? Similarly, moles of products increase with time, right? So can I say your reactants, they disappear with time? Absolutely, the reactants, they disappear with time. Similarly, if I talk about products, your products, they get appeared with time. Products appear with time. Products get formed with time. Okay? So reactants, they disappear with time. Product, they get formed with time. Right? So my dear students, tell me just one thing. Tell me just one thing. If I use the term rate of disappearance, if I use the term rate of disappearance, if I use the term rate of disappearance, so is this term going to be for reactant or product? Disappearance. Reactants disappear with time. So this is going to be basically for the reactants. Rate of disappearance. For example, I want to calculate rate of disappearance of A. A is my reactant here. Rate of disappearance of A. How exactly you are going to write this rate of disappearance of A? Since I'm using the term disappearance, I'll be starting with minus sign. This minus represents disappearance, right? Okay, then I'll be writing change in the concentration of A divided by time interval delta T. This is the mathematical representation of what? This is the mathematical representation of rate of disappearance of A. Okay, mathematical representation of rate of disappearance of A. Similarly, for example, I want to calculate rate of disappearance of B. Let's say I want to calculate rate of disappearance of what? Of B. Rate of disappearance of B. B is again the reactant. I'll be starting with a minus sign. Change in the concentration of B divided by time interval delta T. Similarly, my dear students, if I want to calculate rate of appearance, either you call it as appearance or you can call it as formation. Rate of appearance or rate of formation of C. I'll be starting with a plus sign. Then I'll write change in the concentration of C divided by time interval delta T. In the similar way, for example, I want to get the rate of appearance, or you can call it as the rate of formation of what? Rate of appearance or rate of formation of what? Of D. It's going to be plus change in the concentration of D divided by time interval delta T. Okay. So this is how you guys are going to write the rate of appearances and rate of disappearances of reactants products respectively. Okay. So first thing was the rate of disappearance, second was rate of appearance. Now there comes something as rate of reaction. Rate of reaction. One was your rate of disappearance. That was defined for the reactant. One was your rate of appearance. That was defined for the product. One is the rate of reaction. That is defined for the reaction. Okay. This term, it is not defined for the reaction. It's defined for A. This is defined for B. This is defined for C. This is defined for D. This term, rate of reaction, it is defined for the overall system. Your system is the reaction now. Okay. So rate of reaction is equal. How do we calculate rate of reaction? Rate of reaction is calculated as, the rate of disappearance or appearance of a reactant or product divided by stoichiometric coefficient of a reactant or product. That's how you calculate the overall rate of reaction. That's how you calculate the overall rate of reaction. My dear students, this term is going to give you the idea about the rate of disappearance of A. With what rate A disappears, with what rate B disappears, with what rate C gets formed, with what rate D gets formed. But that particular term is going to give you the rate, overall rate of the reaction. Overall rate of the reaction. How do you get the rate of the reaction? Rate of disappearance or appearance of a reactant or product divided by what? Divided by stoichiometric coefficient of reactant or product. See guys. So I can write rate of reaction is equal to. Let me tell you, you can define rate of reaction with respect to A. You can define rate of reaction with respect to B. You can calculate rate of reaction with respect to C. You can calculate rate of reaction with respect to D as well. Right? And when you calculate rate of reaction with respect to A is my reactant. So I'll use the term rate of disappearance of A. How do I write rate of disappearance of A? Minus delta A upon delta T. This is rate of disappearance of A divided by stoichiometric coefficient of A is N1. So I'll be writing minus 1 divided by N1, change in the concentration of A divided by time interval delta T. So this particular term is going to give me the overall rate of the reaction. This particular term is going to give me the overall rate of the reaction. Similarly, my dear students, we can calculate rate of reaction with respect to B as well. And when you calculate rate of reaction with respect to B, B is again the reactant. So you'll be starting with minus sign. 1 upon. Here it was N1. Here it should be N2. Change in the concentration of B divided by time interval delta T. This particular term again is going to give me what? This is giving me the rate of the reaction. Similarly, you can calculate rate of reaction with respect to C as well. Since C is the product, so I'll use the term rate of appearance of product. Rate of appearance of product. So that means I'll be starting with a positive sign. 1 divided by stoichiometric coefficient here is N3 and change in the concentration of C divided by time interval delta T. Right? So this again gives me rate of reaction only. Similarly, rate of reaction in terms of D, how you are going to calculate? Plus 1 upon N4, change in the concentration of D divided by time interval delta T. So this particular term also is going to give me the rate of reaction. See guys, this term, this term, this term and this term. Do you see anything common here? Delta T, delta T, delta T, delta T. So basically, I'm calculating the rate of reaction. No doubt I'm calculating rate of reaction with respect to A, with respect to B, with respect to C, with respect to D. But I'm calculating rate of reaction in the same time interval. Right? I'm calculating with respect to A in the time interval delta T. I'm calculating rate of reaction with respect to B in the same time interval delta T. Rate of reaction with respect to C in the same time interval delta T. Rate of reaction with respect to D in the same time interval delta T. And the rate of reaction in a particular interval of time is always fixed. It's always constant. Rate of reaction in a particular instant in a particular time interval. Right? Rate of reaction in a particular time interval at a particular temperature, that's always constant. What does that mean? That means whatever value of rate will be coming out to be from here, same value will be coming out to be after solving this particular term. Same value of rate you'll get after solving this particular term. Same value of rate you'll get after solving this particular term. So, if I quickly summarize it. So, my dear students, for example, you have got the reaction N1A plus N2B. It gives N3C plus N4D. This was my balanced chemical equation. Now, rate of the reaction with respect to A. How you are going to write it? A is a reactant. Reactants disappear with time, so start with minus sign. 1 upon N1. Change in the concentration of A divided by time interval delta T. With respect to B, it's minus 1 upon N2. Change in the concentration of B divided by time interval delta T. With respect to C, it's going to be plus 1 divided by N3. Change in the concentration of C divided by time interval delta T. With respect to D, it's going to be plus 1 upon N4. Change in the concentration of D divided by time interval delta T. You take any value, you solve it, you are going to get the rate of the reaction. You are going to get the rate of the reaction in terms of moles, liter inverse. For example, time is in seconds and second inverse. Okay, perfect. Perfect, guys. And this particular equation over here, you call it as the differential form of rate. You call it as the differential form of rate. Differential form of rate. Now, if I ask you what is the difference between rate of disappearance and rate of reaction, talk in terms of expression. When we write rate of disappearance of reactant, we do not divide with the stoichiometric coefficient. When we write rate of reaction, we divide with the stoichiometric coefficient. Yeah? Right, people? Similarly, if I ask you, in terms of expression, what is the difference between rate of appearance and rate of reaction? When we write rate of appearance, we do not divide with the stoichiometric coefficient. But when we write rate of reaction, we divide with the stoichiometric coefficient. Perfect. For example, you have got the reaction like this. N2 gas plus 3 times H2 gas. It gives 2 times NH3 gas. Do you know in your NEET 2022, this was the question asked? We were just supposed to write the differential form. We were supposed to write the differential form for this particular reaction. Okay? And I believe you can easily make the differential form. Write the differential form in terms of, write the rate in terms of N2. Start with minus sign. 1 divided by, stoichiometric coefficient is 1. Change in the concentration of N2 divided by time interval delta T. Similarly, with respect to H2, H2 is the reactant again, so minus 1 by 3. Change in the concentration of H2 divided by time interval delta T. Similarly, with respect to NH3, so start with plus sign, 1 divided by 2, change in the concentration of NH3 divided by time interval delta T. So this is the differential form of rate for the equation which I gave you, and all these 3 terms over here, they are going to give you the rate of the reaction in the same time interval delta T. This was with respect to N2, with respect to H2, with respect to NH3, and all the terms are going to give you the same value. Okay, all the terms are going to give you the same value. I believe this is clear to everyone. Now, my dear students, understand and remember, I'm marking a point over here. For a homogeneous gaseous phase reaction, for a homogeneous gaseous phase reaction, for a homogeneous gaseous phase reaction carried out at constant temperature, carried out at constant temperature, carried out at constant temperature. Remember, rate of the reaction is expressed. Rate of the reaction is expressed in terms of pressure as well. In terms of pressure as well. What is meant by this particular statement? Let's try to understand. See, guys. For example, imagine that you have got a reaction like this. N1A gas plus N2B gas. For example, it gives N3C gas plus N4D gas. This is my reaction in which all the reactants and products, they are in gaseous phase, right? So I'll be calling this particular reaction as the homogeneous gaseous phase reaction. And I'm assuming this homogeneous gaseous phase reaction is carried out at temperature T. This homogeneous gaseous phase reaction is carried out at temperature T. Okay. Now, my dear students, when you talk about the ideal gases, do ideal gases follow this equation? PV is equal to nRT? Ideal gases, they follow this equation. PV is equal to nRT. Okay. Now, people, you can write it like this. P is equal to N divided by VRT. P is equal to N divided by VRT. What is this N by V here? N by V, moles per unit volume. You call it concentration. So I'll say P is equal to concentration, R and T. What does it mean? It means that when we talk about gases, for gases, your pressure, for gases, pressure as well as concentration. For gases, pressure as well as concentration, both the terms are defined. We define concentration of the gas as well. We define pressure of the gas as well. So for gases, pressure as well as concentration are defined. So let me write it over here. For gases, pressure as well as concentration is defined. Now see, so if for gases pressure as well as concentration is defined, and we know concentration of reactant as well as products, they change with time, as well as pressure of reactants and products, that also changes with time. Concentration of reactant and products change with time. Pressure of reactant as well as products, it also changes with time. So when you talk about the homogeneous gaseous phase reaction which is carried out at constant temperature, you can calculate rate either in terms of concentration or you can calculate rate in terms of pressure. How exactly? Let's get to know. See guys, rate of reaction. Tell me, rate of reaction in terms of A, it's going to be -1 divided by N1, change in the concentration of A divided by time interval delta T. With respect to B, -1 upon N2, change in the concentration of B divided by time interval delta T. With respect to C, it's going to be +1 divided by N3, change in the concentration of C divided by time interval delta T. With respect to D, it's going to be +1 divided by N4, change in the concentration of D divided by time interval delta T. You call it as a differential form of rate, right? What do we call it as? Differential form of rate. Now, as I told you already, if you want to solve any of these terms, right? And if you want to calculate rate of reaction by solving any of these terms, you'll be getting the units of rate in moles, liter inverse. I'm assuming time in seconds, so second inverse. Okay. Now guys, we can do one more thing. As I told you a few minutes back, pressure is equal to concentration multiplied by R multiplied by T. If I write PA will be equal to concentration of A, RT. If I talk about PB will be concentration of B, RT. PC, concentration of C, RT. PD, concentration of D, RT. So what exactly am I going to do? I'll be writing R is equal to -1 divided by N1 delta concentration of A. Instead of concentration of A, it's going to be pressure of A divided by RT, and already you have delta T over here. Similarly, -1 upon N2 delta change in, instead of concentration of B, it's going to be pressure of B divided by RT multiplied by delta T. Similarly, in terms of C, it's going to be +1 divided by N3, change in the pressure of C, RT and delta T. In terms of D, +1 upon N4, change in the pressure of D divided by RT multiplied by delta T. If you look at all these terms, do you see anything common here? RT gets cancelled out. And when this RT gets cancelled out, what do we get? I'll be getting rate of reaction like this. -1 upon N1, change in the pressure of A divided by time interval delta T is equal to -1 upon N2, change in the pressure of B divided by time interval delta T. In terms of C, it's going to be +1 upon N3, change in the pressure of C divided by time interval delta T. In terms of D, it's going to be +1 upon N4, change in the pressure of D divided by time interval delta T. My dear students, you have made the differential form of rate in terms of what? In terms of pressure. So whenever you see a gaseous phase reaction, for gaseous phase reactions, you can calculate rate of reaction in terms of concentration, or you can calculate rate of reaction in terms of pressure. And if you use this term, or this term to calculate rate of reaction, okay, understand the units of rate are going to be in what? See, Pressure in the numerator, time in the denominator. Imagine pressure is in ATM. Imagine pressure is in ATM. Imagine time is in seconds. So it's going to be ATM second inverse. So whenever you are supposed to calculate rate of reaction, first you need to have a look whether you need to calculate rate of reaction in terms of moles per liter per second, or you have to calculate rate of reaction in terms of ATM second inverse. Accordingly, you'll use the formulas. If this is clear to everyone, let me know once in the chats with some thumbs ups. Then I'll show you certain questions by means of which you'll understand all of this in detail. Is it clear, guys? Is it clear? Quick. Perfect. Let's try to see what kind of questions can be asked out of the concepts which we have discussed over here. And I believe you can easily solve those questions. The first question, my dear students, which we have on the screen. Look at the question carefully and see what are we supposed to calculate. Look at the question quickly and see what do we have to calculate. As far as this particular question is concerned, if the rate of appearance of O2 is this much, then calculate the rate of disappearance of N2O5. A very simple and basic question. Understand. Just understand one thing. We are given with a balanced chemical equation. Yes, we are given with a balanced chemical equation. Whenever a question is asked on the base of disappearance, on the base of appearance, or whatever, just do one thing first of all. Write the differential form of rate in the beginning itself. Write the differential form of rate in the beginning itself. Say, rate of reaction with respect to N2O5. It's going to be minus 1 upon 2. Change in the concentration of N2O5 divided by time interval delta T. Write the rate of reaction in terms of N2O4. It's going to be plus 1 upon 2. Change in the concentration of N2O4 divided by delta T. Okay. With respect to O2, it's going to be plus 1 upon. Stoichiometry coefficient is 1. Change in the concentration of O2 divided by delta T. This is something which I call as differential form of rate. This is my differential form of rate. Now see in the question, what are we given with and what are we supposed to calculate? Look carefully, guys. If the rate of appearance of O2, how do you write the rate of appearance of O2? How do you write the rate of appearance of O2? You know it. Rate of appearance of O2. Whenever you want to write appearance, you're not supposed to divide with the stoichiometric coefficient. Whenever you want to write disappearance, you're not supposed to divide with the stoichiometric coefficient. So rate of appearance of O2 will be equal to, since it's appearance, so I'll be starting with plus sign, right? Plus sign simply. Change in the concentration of O2 divided by delta T. This is what you call as the rate of appearance of O2. And as per the question, this value is given to me as 0.5 moles liter inverse second inverse. What am I supposed to calculate? I'm supposed to calculate rate of disappearance of N2O5. How do we represent rate of disappearance of N2O5? Like this. Minus delta N2O5 divided by delta T. This is what we call as the rate of disappearance of N2O5. This value we are supposed to calculate. Rate of disappearance of N2O5. This is something which we are supposed to calculate. Now, in this differential rate, in this differential form of rate, I'll be selecting two terms. The one whose data is given and the one whose data is to be calculated. Whose data is given? O2. So I'll be selecting this term and I'll be selecting N2O5 term. I'll be equating just these two terms. When I equate these two terms, I get minus 1 by 2 delta N2O5 divided by delta T is equal. This comes out to be plus delta O2 divided by delta T. Correct? This 2 can go here. It becomes minus delta N2O5 divided by delta T is equal. This becomes 2 times 2 times delta O2 by delta T. Delta O2 by delta T is 0.5. 2 times 0.5. The value comes out to be 1 mole liter inverse second inverse. Correct? And what do you call this particular term as? Look carefully. What do we call this particular term as? This particular term is called as rate of disappearance of N2O5, and this is something which I was supposed to calculate. So rate of disappearance of N2O5 I got to know as 1 mole per liter per second. Is it clear? Is it clear, people? Let me know once in the chats quickly. If it is clear, look at this one. If it is clear, then look at this one. The second question which is on your screen. The question is, for the following reaction, a curve. For what? For concentration versus time is given for this reaction. Calculate the rate of reaction in the interval 5 to 15 seconds. Interval is given 5 to 15 seconds. So in this time interval, 5 to 15 seconds. In this time interval, 5 to 15 seconds, I'm representing this time interval with delta T. This time interval, 5 to 15 seconds, means 10 seconds. This is our interval. So in this time interval, we are supposed to calculate the rate of reaction. Look at the time interval, it's big, right? So we are basically supposed to calculate the average rate of reaction in the interval 5 to 15 seconds, correct? Now, first of all, look at the graph. With the time, concentration is decreasing. With the time, concentration is decreasing, right? So this particular graph has to be valid for the reactant. And because we know, when it comes to reactant, the concentration of reactant decreases with time. So this is the graph which is valid for reactant. And my reactant here in this reaction is NH3. So this is the graph which is valid for NH3, right? This is the graph which is valid for NH3. So what I need to do? I need to calculate rate of reaction. And let's calculate it with respect to NH3. Start with minus sign. 1 by 2. Change in the concentration of NH3. Divide by what? Divide by time interval delta T. So it's going to be minus 1 by 2. Change in the concentration of NH3. See, at 5 seconds, the concentration of NH3 was 0.6. At 15 seconds, the concentration of NH3 is 0.2. So this is the initial concentration of NH3. This is the final concentration of NH3. So final minus initial. Delta NH3. Change in the concentration of NH3. It is final concentration minus initial concentration divided by time interval is 10 seconds. Right? So rate of the reaction, you can solve it from here. Minus 1 by 2. This will come out to be minus 0.4, which comes out to be plus 0.4 divided by 10. So the value is 0.2 divided by 10, right? 0.02 moles liter inverse second inverse. This is your rate of the reaction. Am I clear with this? Am I clear with this? This is something which you are supposed to calculate. Rate of the reaction in the interval 5 to 15 seconds. And we did it, right? It's done and dusted. It's done and dusted. Okay, it's done and dusted. See guys, here you have got two questions. These are the two questions which are given to us. So try to understand how do we solve these two questions. Perfect. Look at these two questions. We are given with a reaction. The reaction is given. We are something is to be calculated. Rate of reaction, rate of disappearance, appearance, whatever is to be calculated, leave that aside. Leave that aside. Just do one thing. First of all, the reaction that's given to me, write its differential form of rate. Write its differential form of rate. With respect to H2O2, minus 1 by 2, sorry, minus 1 by 1, minus 1 by 1, change in the concentration of H2O2 divided by delta T, this is rate of reaction in terms of H2O2 is equal. In terms of water, it is plus, stoichiometric coefficient is 1, so 1 by 1, change in the concentration of H2O divided by time interval delta T is equal. With respect to O2, you'll be starting with plus sign, 1 upon stoichiometric coefficient. So 1 upon 1 by 2. 1 upon 1 by 2 comes out to be 2. Change in the concentration of O2 divided by delta T. You call this as a differential form of rate. And every term here is going to give us rate of reaction in terms of moles per liter per second. Okay. Now, some data is given to me as per the question. If the concentration of H2O2, changes from 0.5 molar to 0.05 molar. In what time? In 15 seconds. So this is the initial concentration of H2O2. This is the final concentration of H2O2. And concentration of H2O2 is changing from 0.5 to 0.05. In what time interval? In 15 seconds. In 15 seconds. What are we supposed to calculate? Rate of reaction. See guys, all these terms here, first term, second term and third term, all these three terms here, they are going to give me the rate of reaction. Now, which term am I going to select over here in order to calculate rate? See, whose data is given to me? The data of H2O2 is given to me. So which term among these three terms I'm going to pick over here? I'll be picking H2O2 term. So rate of reaction, I'll be calculating with respect to H2O2 minus times. Change in the concentration of H2O2 will be equal to final concentration of H2O2 minus initial concentration of H2O2 divided by time interval. That's 15 seconds. That is 15 seconds. Okay. So this is going to give, when you solve this term is going to give me the rate of the reaction in terms of moles, later inverse, second inverse. So first question is done. Second question, calculate the rate of appearance of O2. What is meant by rate of appearance? Rate of appearance means plus appearance of O2. O2 is the product, so I'm starting with plus. Since we are talking about rate of appearance, so nothing to do with stoichiometric coefficient. So plus delta O2 upon delta T. This is what you call as rate of appearance of O2. This term is to be calculated. This term is to be calculated. Rate of appearance of O2 is to be calculated. Now, again use the differential form. Now in the differential form, use two terms. First term, the one whose data is given and the one whose data is to be calculated. So just equate these two terms. When you equate these two terms, what do I get? I get minus delta of H2O2 divided by delta T. Divided by delta T has to be equal to 2 times 2 times delta O2 divided by delta T. You can take this 2 over here in the denominator. It will be minus 1 by 2. Change in the concentration of H2O2 will be equal to final concentration of H2O2 minus initial concentration of H2O2 divided by time interval is 15 seconds is equal to, it becomes delta O2 upon delta T. What do you call this delta O2 upon delta T as? This delta O2 upon delta T is what I call as the rate of appearance of O2. So here you will be getting the rate of appearance of what? Of O2. In what? Its units will be moles, liter inverse, second inverse. It is just the matter of calculation now. Solve it. Get the rate of appearance of O2 in moles per liter per second. Yes? Clear to everyone? So both the questions are done. One was your rate of reaction. One was your rate of appearance of O2. Okay, guys? Let me give you one more question. For example, you have got a question like this. Let's say x times A gives y times B. X times A gives y times B. This is my reaction. X and y, these are the stoichiometric coefficients of A and B. X times A gives y times B. As per the question, given that log of minus dA upon dt is equal to log of plus dB upon dt plus dB upon dt plus 0.3 plus 0.3. As per the question, find x and y. As per the question, find x and y. Find x and y. Now, how exactly we are going to solve this? Find x and y. First of all, let's try to do one thing. The reaction that's given to me. Let's write its differential form. When you write the differential form in terms of A, you'll start with minus 1 upon x. Change in the concentration of A divided by time interval delta T. You can write it with respect to y, but you'll start with plus sign 1 upon y, and it's going to be change in the concentration of B divided by time interval dt. This is my differential form of rate. Okay? What do I need to get? I need to calculate x and y, right? In order to calculate x and y, I will have to use this given data. What is this given data all about? Look at it carefully. This term is in terms of log. This term is also in terms of log. But this term is not in terms of log. So let's do some basic maths. Since the last term is not in terms of log, let's try to convert the last term in logarithmic form. So instead of 0.3, I can write a log of 2 to the base 10. Here also the base is 10. Here also the base is 10. Okay. Instead of 0.3, what did I write? I wrote log of 2 to the base 10. Now guys, it's pretty much simple. Every single thing is clear. It's log of minus dA upon dt. Log of minus dA upon dt is equal to log of m plus log of n. Log of m plus log of n. Log of m plus n means log of m into n. So it is log of m into n. So 2 multiplied by this term. Okay, 2 multiplied by this term. Perfect. So what you need to do, if you apply NT-log on both the sides, if you apply NT-log on both the sides, here it's log, apply NT-log on both the sides, what do you get? You get minus dA upon dt is equal to 2 times d of b upon dt. Correct? Take the 2 in the denominator, so it will be minus 1 by 2 d of a upon dt is equal to d of b divided by dt. Correct? Now, I got two equations basically. Equation 1, equation 2. My dear students, I would want you guys to compare equation 1 and equation 2. d upon dt, d upon dt. Minus 1 upon x, minus 1 upon 2. X value directly is equal to 2. Here, db upon dt, db upon dt. 1 upon y, 1 upon 1. So y value over here is 1. This is something which you were supposed to calculate. X value 2, y value 1. Is that clear? Is it clear, people? Quickly in the chats. Is it clear? Perfect. Perfect. Let's move on to one more question. One simple and basic question over here again. And I believe you can solve this question easily as well. See guys, as far as this particular question is concerned, we are given with the reaction. This is the reaction. This is some data that's given to me. Some data. Find the relation between K1, K2, K3. This is K1, K2, K3. We have to get the relation between K1, K2, K3. See, it looks some huge question, difficult question, but it's not. It's not. Rakesh, this chapter is going to take some 3 sessions. Okay? 3 sessions is going to take. A coordination chemistry topic ma'am is already doing. Sonali ma'am, she has started coordination chemistry on this channel itself. All right. See guys, this is the reaction, a balanced chemical equation that's given to me. Now, rate of reaction with respect to N2O5. How much that is going to be? Minus 1 upon 1. You can write change in the concentration of N2O5 divided by dt. You can write delta this, delta t as well. I'm writing dd because the given data is in terms of d. Right? Now, what will be the rate of reaction in terms of NO2? NO2 is the product, so start with plus sign 1 upon 2. It will be d of NO2 divided by dt is equal to O2. It's going to be plus 1 upon stoichiometric coefficient. 1 upon 1 by 2 is d, is 2, d of O2 upon dt. Correct? This is something which I call as something which I call as differential form of rate. Now, my dear students, look at this particular term, minus d of N2O5 by dt. D minus d of N2O5 by dt. This is given to me as per the question. K1 N2O5 is equal to NO2 upon dt. D of NO2 upon dt is given to me as, see, 1 by 2 I'm writing as such. D of NO2 upon dt is it nothing but K2 multiplied by N2O5. Okay. Now, 2 times d of O2 upon dt. D of O2 upon dt is nothing but K3 multiplied by concentration of N2O5. So N2O5, N2O5, N2O5 cancels out. So I got to know K1 is equal to K2 divided by 2. That's equal to 2 times K3. If I multiply throughout by 2, this becomes 2 times K1. This becomes K2. This becomes 4 times K3. So this is your relation between K1, K2 and K3, which you were supposed to calculate. Got it? Got it, people? Is it clear? One question I'm giving you as the homework, and this is your question, guys. This is your question which I'm giving you as the homework. You are going to let me know the answer of this particular question. These are 2 questions. First, you have to calculate rate of reaction in terms of moles, liter inverse, second inverse. Then you have to calculate rate of reaction in terms of ATM second inverse. This is your homework question. Its answer I would want in the comment section of this particular video. Okay? Right? Perfect, guys. So this was all for today. This was your lecture 1 of chemical kinetics. The second lecture will be scheduled on Tuesday, right? On Tuesday, 7 p.m. we'll have the second session of the chapter chemical kinetics. I believe all the concepts, all the things which I taught in this particular session, I hope every single thing is absolutely clear to you, because everything I talked about every single thing in detailed manner, right, from the basics itself. I believe it would be clear to you. Okay, so do let me know in the comment section at the end of this particular session if you liked it or not. Okay, so take care, God bless you all guys, and see you. Bye-bye.